Okay. Hello, everyone. I hope you all started a great day. Today, we are going to talk about the switches, transistors, most specifically the MOSFET and BJT. And we try to remember what we learned about the MOSFET and BJT before, what are the characteristics or how we can use them, and what are the kind of like the main application of each of them. And we are gonna go through like the using of the MOSFET as a logic circuit. In logic circuit, we are gonna talk about the BJTs and how we can use them in amplifiers like Class A, Class B, and Class AB, as you are gonna see, and you have to actually design your own in the lab assignment too. Now, let's basically start with the MOSFET. If my PowerPoint works for me. Yeah. MOSFET is a basically PNP or NPN a semiconductor. So you have two junctions in MOSFET. And you are gonna trigger MOSFET based on the voltage that you apply to the gate. As you know, we have three terminals in each MOSFET. One, we call it drain. Another one is source. And the third one is the gate. As I mentioned, the gate is the one that controls the state of our MOSFET. So is it conducting or how much current is conducting? Is it in a saturated mode or active mode? Or if we cut the gate, it would be in the cutout mode. Now, as we said, because we have three semiconductors and we have basically two junctions between them, we could have two types of MOSFETs. Either we have PNP, kind of like setting for our semiconductor, or we have NPN. If we have NPN, we call it N channel MOSFET or NMOS. Okay. If we have PNP, we call it P channel or PMOS. So basically, the semiconductor connected to the drain and source defines what type of MOSFET you have. Okay. Now, the middle one, we call it the basically we call it the channel one. Okay, so in the NPN, the P is the channel. It's kind of like obvious because this is where you can control and you can actually channel the current from drain to source. Okay, in a schematic, as you can see, we have two types of symbol for each of the MOSFETs because we have two types of them. One is the enhancement type. Okay, this MOSFET is normally off, so when you trigger it, it is going to be turned on. We also have another type for each of the NMOS and PMOS, which is depletion type, which is normally on, and when you trigger it, it's turned off. Okay, so this is the difference between the two. Now, in NMOS, as you can see, with the arrow in the middle of the symbol, the current flows from source to drain. Okay, and in the PMOS, it goes from drain to source. Okay, so this is basically the general understanding of the PMOS and how we can show it in the schematic of in our circuit. Any question from the beginning of the discussion? No? Now, each MOSFET has an IV characteristics, which relates the current that passing between the drain and source, either way based on the PMOS and NMOS, and the voltage between the drain and source. So why we call it a drain current? Because the drain current and source current are equal, so it doesn't matter. So we call it current of the drain in IV characteristic, okay, versus the voltage across drain and source. Okay. Now, as you can see, when we apply a voltage between gate and source, okay, the voltage between gate and source, we can activate or trigger our switch. So if we don't have a voltage, that means the switch is off. We are talking about the enhancement. Okay, so we are going to focus on that because we are going to work with that type of MOSFET in our plan. So when we don't have a voltage between gate and source, the switch is off, so we call it a cutoff mode. Now, remember, it's not like every positive voltage would turn on the signal, the switch. There is a threshold. You have to have a certain amount of voltage between gate and source above that threshold, which is defined in a datasheet. And basically, you can actually test that when you have the switch, so you can see, okay, how much voltage you have to apply between the gate and source, so the switch is conducting, okay? So, as you can see, below that threshold, in the curve, you can see we don't have any current here. We don't have any current. Current of the drain is 0, so we call it cutoff. Now, if you start applying voltage between gate and source and go beyond that threshold that we talked about, now the switch starts conducting. At first, okay, when the voltage between drain and source is low, okay, you would have kind of like a linear relation between the current and voltage, the current of the drain and voltage between drain and source. We call this mode a triad mode. Now, you can see that this is not exactly linear, okay, but similar to the diode that we talk about the voltage drop model, okay, constant voltage drop model, we can kind of like assume it's a linear and we ignore that exponential like knee on the curve. Is that clear? Are we good on that? Now, if the voltage across drain and source, the voltage across drain and source exceeds a certain threshold, which we call it the VDS saturation. Okay, here. Now the currents get stabilized. Who can tell us why a certain amount of voltage, okay, the current is saturated and gets constant would not vary? Anyone can tell us why after a certain voltage between drain and source we get into the saturation mode? Any idea? Now let's see what is the physics behind it. Let's say we have NMOS. This is the gate. This is source. This is drain. Okay. Without the gate, go ahead. Exactly. Okay, let me repeat what your friend said. So when you apply at the beginning, when you don't have any voltage across gate and source, this P works as a semiconductor works as an insulation. Okay. Now, when you apply a volt, basically means you are applying uh, electrical field, an electrical force between gate and source. So you are basically polarizing that P semiconductor. Then what happened? Same as what we said about the diode. Okay. Now it is start to get polarized. So we are gonna have a channel that the charges can jump through from source to drain or drain to source. Are we clear? Now, for each specific voltage between gate and source, you would have a certain width of a channel. It's not exactly like a smooth like line of a channel. It's normally has a kind of like an exponential curve from physics. Okay, so you have a certain amount, a certain width of the channel that you activated based on the gate source voltage that you applied. Now, when you apply that, then the voltage, this is gonna get kind of like similar to a resistor, okay? But when you apply voltage between drain and source above the saturation, then basically you're forcing, okay, when you are in the saturation VDS, okay, you are basically occupying all the capacity of that channel for transferring the charge. So physically, it cannot exceed that amount of current and that amount of charge transfer. So after that point, when you apply more and more voltage across the drain and source, then you still would have the same amount of the current. So after that, we get to the saturation. Is that clear? Now, when you look at this characteristic curve, the IV characteristic curve, you can see that we don't have just one graph that relates the current and voltage. We have multiple graphs which they are distinguished based on the level of the voltage that you have between gate and source. And as you increase the voltage of the gate and source, you can see that the capacity of conducting the current through the drain and source would increase. So you would have higher amount of current, okay, conducting between drain and source. Is that clear? Now, why is that? Anyone can tell us why is that? Why, if we apply more and more voltage between gate and source, we have higher amount of current passing between the drain and source. The voltage that we say is between gate and source. The current is between drains. So let's say we have the same amount of current, the same amount of voltage between drain and source. This is constant, okay? VDS1. Now, if we apply VGS1, we have this amount of current. If we apply higher voltage between gate and source, VGS2, now we have more current. The VDS is constant, but the current increased. Why? Now it again comes back to what we discussed here. What happens if you apply more voltage between gate and source to that channel? Sorry? The more electrons is based on the capacity for the width of that channel. Now, when you apply higher voltage between gate and source, you apply a more powerful electrical field between the gate and source, that means you have more force for polarization. That means you are increasing the width of that channel. Now, when the width of the channel increase, that means we have more capacity to pass charges between drain and source. That means the level of the current increases. Are we good? So, as you can see, let's summarize that. Below a certain threshold of the voltage between gate and source, the middle semiconductor, either P or N, would cut the current and works as an insulator. Okay. When you apply a certain amount above that threshold between gate and source, the voltage between gate and source, now you are polarizing that semiconductor. So you open up a certain channel that the charges can jump through between drain and source, either way. Okay. Are we good? Now, when you apply higher channel, higher voltage between the gate and source, you have wider channel. So you have more capacity to transfer charge between drain and source. At the beginning, before you saturating your current, your channel, as you increase the voltage between drain and source, approximately the current that passing through would linearly increase. But after a certain point, when you reach the full capacity, you occupy the full capacity of that channel. Now it doesn't matter how much you apply the voltage higher and higher, okay? You don't have any capacity to go further in respect to the current. So it gets saturated, meaning you have a constant current regardless of the voltage between drainers. Are we good? This is the characteristics of the MOSFET. Now, we normally use MOSFET in the saturation. Anyone can tell us why? One reason it's related to the application of the MOSFET. Another one is basically relates to the accuracy of what we need. When you say more stable, what do you mean? No. It is true what you said. What I'm looking for was like a root reason of that instability or like weak stability. Okay. Now, the second reason that you said is correct. We normally have use the MOSFET as a switch. So it's turn on and turn off. We don't use it as an amplifier. Okay. So it's better to have a constant current. So either it's on and conduct a certain amount of current, or it's off and does not conduct any current. Okay, so this is one reason application regarding the application of the MOSFET that we wanted to like keep in the saturation mode. Okay, keep the MOSFET in saturation. Another one that your friends mentioned is because we wanted a more stable performance out of our MOSFET. Now, why, if we go to the triad mode, is not, we don't have the kind of strong characteristics regarding the stability, is because in real world, we never have a pure voltage between drain and source. So we have variations, which is not under your control. We have noises, we have like, fluctuations between the on the voltage between drain and source. So if you can control the voltage between drain and source, that means you can control the current. Okay, so that's one reason. Another reason is that the semiconductors, when you want to model it, there is a resistance in the semiconductor, which is highly sensitive to the temperature. Okay, so as the semiconductors start working and switching, the temperature goes higher and higher, and probably you see that normally MOSFETs using a heat sink because it's actually gets to the very high temperature. And if we have high temperature, that means the characteristics of a semiconductor is changing. So you start with a specific, like a certain characteristics, and during the time you would end up with a different test for your MOSFET. So if you are in a triangle mode, basically, even if you set that perfectly at the beginning, later on you are going to have a deviation. Is that clear? So two reasons. One, the fluctuation and uncertainty of the voltage between drain and source. Another one is the thermal effect. So we wanted to keep our MOSFETs in a saturation mode. They far from that need. Okay, so we don't want it to be near that part. Okay, near this curve of VDS saturation. We want it to have a proper distance from that point. Now, in order to calculate the current of the drain, which is basically our output, versus the voltage between gate and source, which is basically our input, okay, you can use this formula, which is the current is equal to the Kn, which is the transconductance parameter of your MOSFET given in the datasheet. Although you can actually very easily measure that, and based on the measurement, you can find that Kn. It's very easy, okay? And the value is going to be the voltage between gate and source minus that threshold that we talked about, the squared times that Kn. Now, this is the current that you have in your drain. Okay, now you might see that we have a lambda here. This is a function of the width of the channel. You don't need to consider that. It's not going to affect much when in the lab assignment that you have, and even in the design that you want to have, is not that sensitive. So you want to consider that lambda, okay? But it's good to know that there is an effect of the width of the channel, the characteristic of that channel in the middle semiconductor, okay, that would affect the current in a drain beside the voltage between gate and source. Are we good? So this is how you can calculate the current based on the VGS. Now, how you can measure that in the lab, if you wanted to measure that Kn in the lab, you have to inject a certain voltage in the between the gate and source, connecting the voltage supply between gate and source. You start to go up, increase the voltage until you see that the MOSFET is turned on. That voltage will be the threshold. Are we good? Now, after that, you are gonna connect an ammeter in series with your drain. Okay. Now, when you pass that threshold, you're applying a voltage between gate and source, which you know what is the amount of voltage. Okay. And you also measuring the current passing through the drain. Okay. So now you have the values of these two voltages, and you have the value of the current. Easy math. You can find the Kn of your specific MOSFET that you're using. Is that clear? So this is how you can calculate the Kn based on your measurement. Now, remember, when you want to, like, if you want to do that, okay, which you have to actually, if you want to do that, you should not use the MOSFET without a state resistor connected in series with the drain. So you have to basically limit the current so you won't burn out your MOSFET. Is that clear? So always we use the semiconductors in series with a certain current limiting resistor. Very good. Now, some of the common mistakes when you work with a MOSFET is one is mixing up the pins. The gate is not hard to miss. It's normally the middle gate, okay? But you need to pay attention to not connect the drain and source in the wrong setting, okay? In the wrong places. Now, every MOSFET also, this, please pay attention. Every MOSFET has a bypass current. Okay, so in the event of turn off, when it wanted to turn off, there is a pass to kind of like drive the current, so you won't force a reverse current to your switch. Does that make sense? Is that clear? So you have a bypass diode. Be careful about that. Because if it's conducting and you don't consider that in your circuit design, then you would have a kind of like error in your output. Okay? You normally don't would not have such a problem because you normally use MOSFET. It's not going to be affecting much in the lab assignments, but be aware of that. Okay? The reason is because you normally use a MOSFET as a switch and you have a relatively high voltage between the gate and source and drain and source. So you don't use actually the state of the MOSFET in your circuit. So that reverse current is not on a state that you desire to have. You know what I'm saying? But remember, it is gonna be there and it is gonna affect the performance of your circuit. Is that clear? Are we good? Okay. Another mistake, as we said, is to assume the threshold, the voltage gate source threshold as zero. Just to have a positive voltage between gate and source does not mean that your MOSFET is on. There is a threshold. You need to be above that threshold. Be careful about that. Now, also be careful about what type of MOSFET you use. Okay? If you're using PMOS or NMOS, it would change the direction of the current. And we know by the basic laws of electricity, the current goes from high potential to low. That means the polarity of VDS in PMOS and NMOS is changed. Good. So if you connect the wrong polarity based on the direction of the current, your MOSFET would not work right. Actually, wouldn't work. Is that clear what I mean? The direction of the current between PMOS and NMOS changing, and the current always goes from high potential to low potential. That's basic physics of the current and voltage. Okay, so when you want to like connect PMOS and NMOS, be aware of that. Direction of the current and the polarity of the voltage against the drain and source. Are we good? And basically, you can see when we talk about the PMOS, you can see that we talk about the absolute value of each voltage. But in NMOS, we directly talk about the voltage itself. That is because of that reverse polarity. Make sense? Is that clear? If you don't have any question about MOSFET, I wanted to start talking about the BJT. Any question? No? Good. Now, BJTs are another type of transistor, which is basically bipolar junction transistors. Okay? We normally have three terminal, similar to MOSFET, but different name, and different basically physical characteristics. We have base, which is the control terminal, and we have the collector and emitter, which is the current conducting or power terminals. Are we good? Now, we have two types of BJT based on the semiconductors and the connection of the semiconductor inside that BJT. Either we have NPN transistor, meaning the collector and emitter are N-type and the base is P-type, or we have P and E in reverse. The symbols are given in the slides, and as you can see, again, like the MOSFET, the difference between the PNP and NPN when it comes to the circuit is the direction of the current. So in NPN, current goes from collector to emitter, and in PNP, it goes from emitter to collector. Okay? Now, one of the most important differences that you have to pay attention to between the BJTs and MOSFET is that in BJT, our control signal is a voltage. So we apply voltage between gate and source, and then we turn on our switch to conduct the current between a drain and source. In BJT, the control signal is current. So you have to inject current to the base. Now you trigger the switch, okay? And you have a certain amount of current passing between the collector and emitter in either direction based on PNP and NP. Are we good? This is one of the most important aspects of the controlling the BJT, the difference between the controlling the BJT and MOSFET. Now, BJT also have IV characteristics, which defines the current of the collector, okay, versus the voltage between the collector and emitter. So, if you inject current into the base, you are turning on your BJT, so it will start conducting. So you will start seeing current in the collector, and as you increase the voltage between collector and emitter, your current get increased, which is this mode, and we call it the saturation region. And similar to what we discussed about the MOSFET, after a certain point, the NPN or PNP junction gets saturated, so you can exceed the current. You can go higher in respect to current. So the current gets saturated and gets constant. It doesn't anymore is a function of the voltage between the collector and emitter. So you are going to end up in this region, which we call it the active region. Are we good? Now, same analogy as we had for a MOSFET when we talk about the level of the voltage between gate and source and the amount of current. Same analogy we have here when you increase the current injected to the base, you increase the current or the capacity to conduct the current in a collector. So for higher and higher base current, you would have, when you increase the base current, you would see increase in a collector current. Are we good? Any question about that? No? Okay. Again, we normally use the collector in an active region, in the region that I collector is saturated and is constant. In reality, it's not actually constant. There is a slope, but we can neglect that. Okay, it's a very kind of like low rate of the change under the slope, so we can consider it constant. Okay. Now, so we use the MOSFET, sorry, the BJT in the active region, and why is that? Anyone can remind us of why we use that in an active region? Again, it goes for two reasons as before, application and stability. Can you tell us the application one? The reason regarding the application of the BJT that we wanted to like stay in an active region? Now, what we use the BJT for? What is the application that we use the BJT for? Do you remember? Amplification. So if we want to have amplification, which basically is the amplification between the current injected into base and current we have in the collector. If we have such a purpose, such an application for the BJT, to amplify the base current into the collector current. Now, why we need to stay in the active region? What is the main goal of amplification? What is the main parameters of an amplifier? Yeah. Linearity what? Like what parameter define that? Beta. What is the beta? Is the gain. Correct? In each amplifier, it is asking what the purpose of amplifier. You want to have a certain gain. And you want to have a stable. Okay? So that gain would not vary outside of your control. If you're in a saturation mood, for each a specific amount of base current, you have a specific amount of collector current. So your gain is constant. But if you are in a saturation mood, now your gain is not just there's not just a function of the IB and IC, it also varies based on the voltage across collector and emitter. So when you have a variation in that voltage, now your gain changing. Is that clear? So you don't have proper control in the saturation mood over your gain. Now, the gain, we call it beta. we achieve the ratio of the collector current over the base current. Are we good? And we have a very stable, very good stability in the beta in the active region. Now, I want you to be careful about one thing. When you want to like calculate and design your calculate the parameter and design your circuit, and it's the fact that unlike MOSFETs and any type of FET kind of like switches, the currents between source and between collector and emitter are not actually equal to each other. In MOSFET, okay, the gate was isolated from the PN junction, so it only applied voltage. So there is no injection of the current from the gate. But in BJT, your base is directly connected to the semiconductor. So whatever current you inject to the base, okay, it is injected to the circuit and to the channel between the collector and emitter. Conservation of the energy, which basically in electrical engineering we call it KCL, because whatever current is injected should be equal to the whatever current we drain from that point. Correct? So if you have a current injected from the collector to that semiconductor, to that device, and you also have a current injected from the base, that means the current in the emitter should be the summation of the two. It's a very simple conservation of energy and the conservation of charge. Is that clear? So now we know that the current between the base and collector has a relation. And this one is actually beta IB. So what happened to the emitter current? Emitter current is 1 plus beta base current. Are we good? Now, in practice, the collector current is much higher than the base current because normally we have a beta above like 100 and 200. For example, when you work with the BS 170, okay, is that BS 170? I'm sure. The BJT that you work with, your beta is around 250. Okay, so you can imagine the effect of base current, the basically amount of base current in the emitter current is negligible compared to the amount of the collector. Okay, now when this 1 plus beta gets important, when you want to design your circuit and define the resistors connected to your BJT, okay, because those resistors actually work as the general gain of your amplifier. It would have a role in general gain of your amplifier. And for example, if you have like a 10K resistor in your emitter, the resistor that you see from the base is not that 10K. Makes sense? It's 1 plus beta that thing. Now, because you have 10K, that 1 would become a quiet of a resistance seen from the base. Make sense? Is that clear? So that is important when you want to like design and calculate the amount of resistance that you want to put into the to connect to the emitter, because now the base sees 1 plus beta of that resistor, not just a beta of that resistor. And since normally we use a high amount of resistor, that 1 is quite a number. Is that clear? Are we good? Now, we said that we wanted to stay in an active region because we want a stable beta and a stable gain. How we do that is based on biasing, is using a biasing techniques. Okay, so we make our BJT stay in an active region. We have several type of biasing. One would be the fixed biasing, when you basically use a single resistor and inject the current into your base based on that resistor and VCC. Okay, it's very easy to kind of like implement, very cheap, very easy. But since the resistor is changing and it's kind of like varies based on the temperature, it's not a stable way to bias it. Now, another way is to basically give a feedback to our biasing system by adding a resistor into emitter. Okay, that emitter resistor gives like a negative feedback into our system. Now you can see this 1 plus beta that we talk about. Okay, the beta is the gain. The plus one, I don't know if you pass the control system or not. When you have a negative feedback, the general, when you have a negative feedback, GH output input, the general transfer function of the whole system, which defines the input and output, become G over 1 plus GH. Negative feedback has a plus in the formula. Positive feedback has a 1 minus GH. Okay, I don't know if you have the control system in the course, but you can easily kind of like search on that. So this is why we call it a negative feedback. So it gives you a negative feedback and help you to stabilize your bias. But the best way to bias the system is a voltage divider. When you do the voltage divider, okay, in these two biasing, okay, you have a current injected from VCC, and you also have an input current, which is your signal to turn on and off your BJT. So the current in the base is both the current injected from the VCC, your power source, and the input signal. In voltage divider, you set your system in a way that the current from VCC goes through this resistor. It only set the voltage of the base, and now the only current that is injected to the base is the signal that you wanted to like inject to the circuit. So this is the very good biasing system, and it keeps you from the variation, stabilize your biasing in a very good region in active mode. Is that clear? Are we good? Any question about that? No? Okay, BJT mistakes. Incorrect base current is a very common mistakes. Wrong operation region, when you don't bias properly your BJT, is another common mistakes. Thermal runaway, as we said, thermal increase in the temperature would affect both your resistance that you have in your circuit and the BJT itself. And lab verification, which I encourage you to always double check the biasing to make sure you are still in active region. Are we good? I'm gonna go very fast on the Class A amplifier. We already talked about that in the circuit lab, and I'm gonna talk about that in a video. Okay, Class A amplifier uses one BJT, and it the BJT works all the time through the whole 360 degree of your input signal. Okay? And you have like a linear gain, but it's very poor in efficiency. It's maximum like 30 or 25 to 30%, and you never gonna get that margin. Is normally you best you can get is like 14% efficiency. Class B amplifier uses two NMOS and PMOS in series. Each of them are responsible for half of the your signal cycle. So one conduct to the positive, another conduct to the negative half cycle. The problem, this would have a higher efficiency, but the problem for that is that when you wanna to like change between the NMOS and PMOS, because it cannot instantly cut the current, you are gonna have an overlap before the top one is turned off and the in the time of turn off of the top one and the turn on of the bottom one, and vice versa. You are going to have overlap, which create a distortion in the zero crossing part of your signal. Now, how you can do that? By class AB amplifier, which basically fix the bias, the voltage between base and emitter in two BJTs, and take care of that overlap problem. Are we good? Any question about that? Now, I have a very detailed kind of like explanation. I don't know if you've gone through the video or not. Okay. I talked in more detail about each component of this amplifier and the BJT itself and the MOSFET itself. Okay. So go over that video. If you have any question, let me know. Are we good? Any question? I am going to give you an extension. I will announce an extension for the lab 2. Okay, so you are going to need one day, one lab session. You have enough time to cover that next. Are we good? Yeah, one last question. So how do you verify